Good day, calculus students. I'm going to do a little bit of review of some factorials. Simplify the following. If you don't remember what factorials mean, it means to do this. 5 factorial is do 5 times and then multiply all the numbers counting down to 1. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. 4 factorial is 4 times 3 times 2 times 1. In fact, you can argue we don't need to go to 1. We can stop at 2. And here we get 24. 3 factorial is just 3 times 2. That's 6. 2 factorial is just 2 times 1 if you want to put the 1 there, but it's just 2. 1 factorial is just 1. And by definition, we're going to say 0 factorial is also 1. If you have a ratio of factorials, you could write them out entirely. But this was really a waste of time because you should notice that the 6's and below cancel, leaving you just 8 times 7. So maybe a better way to do this is to start with the larger factorial, which is in the numerator, and count it down until you get to the smaller factorial, and then summarize the rest by putting the factorial sign there. Right? You don't need to write out all the terms. The factorial sign implies that they keep going. And then we get some cancellation, and we have 8 times 7 as a result, and we just get a 56 out of that. So this kind of shows us a way that if you want to write an expression for, say, a factorial, maybe like 12 times 11 times 10, but you want to cut it short, and let's say you only want a partial factorial, 12 through 9 multiplied. Well, then a way you could do that is by dividing factorials. Do 12 factorial and divide it by 8 factorial, and this would represent doing 12 times 11 times 10 times 9, because the 8's and below would have canceled. In general, if you have n plus 2 factorial and you divide that by n factorial, that's really like this case in a more general situation. N plus 2 factorial literally means start at n plus 2, multiply it with one number less, which is n plus 1, and then multiply that with one number less, which is n, and then n minus 1, and then n minus 2. And you would continue this generally until you get to 2. And the bottom would be the same thing, but starting at n. But then, just like above, you're going to recognize that n and below will get canceled. So we really just get out of this n plus 2 times n plus 1. Or if you go the other way around, if the larger factorial is in the bottom, this time I'm not going to write out everything. The smaller factorial I'm going to leave, but the larger factorial, I'm going to start doing the factorial pattern. The next one would be n. Once it matches the one that's up here, I'm going to stop and just summarize the rest with the factorial. N factorials will cancel. So in this case here, we're left with a 1 up top and an n plus 1 in the bottom. These kinds of simplifications will be helpful as we move forward. We're going to learn 2 new tests. The first is the ratio test. The ratio test is going to be a test that's useful when you have sequences that involve factorials or powers that have an n, so like 3 to the n or n to the n. Here's our domination chain. We haven't really been exploring much this end of it. Cases where n is the power, like these 2 cases, or factorials. We've mostly been working in this realm so far with all the tests we've been developing. All right, here's the ratio test. Suppose that a sequence a sub n plus 1 divided by a sub n, this plus 1 is part of the subscript, and you take the absolute value of that ratio and you do a limit, and that limit is k. Depending on what k is, we can make conclusions about the series of a sub n. If k is less than 1, then we're going to be able to conclude that the series is absolutely convergent. If k is more than 1, that the series is divergent. And if k is 1, then the ratio test is inconclusive. You would have to do some other test. All right, so our first example to illustrate this is right here. And notice that there's factorials present. That's almost always a dead giveaway that you should be working with the ratio test. Let's go ahead and just take a quick moment and write out some of these terms, what they would be, and let's assume a starting value of n. If this started at n is equal to 0, you're allowed to do because 0 factorial is not 0, it's 1, so we can plug zeros in safely. You would get a 1 up top and a 1 below, so you just get a 1 as a leading term. Now let n be 1. Negative 2 to the 1, that's just going to be negative. So there's going to be subtraction. 2 over and then 1 factorial. Next term will be plus. It'll be a positive 4 up top when n is 2, and here you have a 2 factorial. Then it's going to be minus 8 over 3 factorial. Plus, next one will be 16 over 4 factorial. You might be wondering, hey, what's this sequence even doing? Which of these dominates which, factorials or exponentials? Factorials dominate exponentials. These factorials are going to outgrow these exponentially growing numerators. It is true that that sequence is approaching 0, so it's possible that the series is convergent. Just some things to think about. Flip these around, by the way. Put the factorial over an exponential. As a sequence, this goes to infinity. So as a series, it's going to be divergent clearly. So it's always helpful to keep this domination chain in mind when you're looking at a new expression. Which one's growing faster than the other? Okay, anyway, let's do the ratio test. We're going to set up a sub n plus 1 over a sub n and then put it in absolute value bars. where this is the a sub n that we're referring to. Now what a sub n plus 1 means is write this expression down, but change all the n's to n plus 1s. So we have negative 2 raised to the n plus 1 over an n plus 1 in parentheses factorial. And then divide that by a sub n. And then put this in absolute value. Okay, so this is our setup for doing the ratio test, and we're going to now simplify this before we do a limit. First of all, the absolute values are going to simply just get rid of the negatives. So really you could write this as just 2 to the n plus 1 over n plus 1 factorial. And instead of dividing by this fraction, I'm going to multiply by the reciprocal. So times, and then flip that denominator over, n factorial over 2 to the n. No negatives needed, absolute value took care of them. Now we want to simplify. Regroup the terms. If you recall, x squared times x cubed is equal to x to the 5th. You add the powers, so you can do this property backwards. If you have a sum up here, you can break up the powers as separate powers on their own bases. I'm going to do that with this 2 to the n plus 1. So we get 2 to the n times 2 to the 1. And I'm also going to put this term right here underneath it. And then I'm going to align the factorials. We have an n factorial over an n plus 1 factorial, which can be written as n plus 1 times n factorial. N factorial and n factorial gone. 2 to the n and 2 to the n are gone. 2 alone in the top and n plus 1 alone in the bottom. So we started with that, simplified it. Now we're going to see what happens as n goes to infinity and determine what this k is. We let n approach infinity. As it does, this does approach 0. This is the k. And then we look at our flowchart. Clearly 0 is less than 1. Therefore, we can conclude that the original series is absolutely convergent. Thus, the original series absolutely converges by the ratio test. This ratio test is nice because if successful, it puts your series directly into this smallest class. Let's do some more ratio test here. Well, first of all, just a quick analysis. Let's make sure that we do have something that's going to 0 as a sequence. Essentially, we can get that negative 1 out of the way. We have a 3 to the n over a 2 to the n. That's like a 3 halves to the n times an n plus 2. This is a growing geometric series. 3 halves, the higher powers. 3 halves is more than 1, so this is getting bigger and bigger. This is getting bigger and bigger, and then we have it alternating. This is going to be a divergent series because the sequence is not going to 0. This sequence is not going to 0, therefore this diverges by the divergence test. But let's go ahead and use the ratio test to confirm it as well. So I'm going to put the original, but change all the n's to n plus 1s, then multiply by the reciprocal of just this. And there's our setup for doing the ratio test. Do a bunch of simplification and rearranging of terms, get rid of these negatives in front of the 3's. The absolute values will take care of that. I'm going to put the 3's over the 3's, and I'm going to break up this 3 to the n plus 1. So we're going to get a 3 to the n times a 3, and then there's a 3 to the n in the denominator. I'm going to do something similar with the 2's. There's a 2 to the n up top and a 2 to the n times a 2 in the bottom. And then I'm going to put the polynomial parts over each other. So we have an n plus 3 up top and an n plus 2 in the bottom. So this is what it simplifies to after the absolute value takes care of the negatives and you rearrange. Let's do some simplifying next. 3 to the n, 3 to the n, 2 to the n, 2 to the n. Careful here you don't do like this, or those n's do not cancel. The addition prevents that cancellation. It still simplifies to a 3 halves times an n plus 3 over n plus 2. And now we do a limit. As n goes to infinity, you can use L'Hopital's rule on this. This approaches 1 over 1. It's also a balanced rational function. So this approaches 3 halves times a 1, which is just 3 halves. This is our k. K is 3 halves. That's more than 1. Right, we're now looking at this case here. Therefore, the series is divergent. Thus, and again, be careful about what you say here. Just don't say thus diverges. I want complete sentences. Don't say it, because it could be referring to a sequence or a series. To say a sequence diverges isn't the same thing to say that a series diverges. The safest thing to do is to write a complete sentence here where you just essentially rewrite this. Thus, this series diverges by the ratio test with our supporting work here. Of course, we also saw that it diverged by the divergence test because the sequence does not go to 0. This next one, this one doesn't have exponentials or factorials, which make me probably want to lean towards one of my other tests. Let's go ahead and try the ratio test, though, just to see what happens. So I'm going to begin by absolute value, replace all the n's with n plus 1's. So really you're going to have an n plus 3 up top over a 4 times an n plus 1 squared plus a 3 times an n plus 1. And then multiply this fraction by the reciprocal of the original. Notice everything here is going to be positive too, so absolute values just aren't needed. There are no negative terms in this particular series. I'm going to write the n plus 3 over the n plus 2, and then here I'm going to do some factoring, and here I'm going to do some factoring. Let's start with the numerator. I can factor an n out, and that leaves a 4n plus 3. And the denominator here, I'm going to factor out an n plus 1. That would leave a 4 times n plus 1, and then plus a 3. So we have n plus 3 over n plus 2. I have an n over n plus 1. Last one is a 4n plus 3 up top. And if I distribute the 4 and then add the 3, it's going to be a 4n plus 7. Alright, now I'm in a good position to do a limit as n goes to infinity. I can really do these one part at a time. This approaches 1, this approaches 1, and this approaches 4 over 4, which is also 1. So this approaches a 1 times a 1 times a 4 over 4. In the end, this is all equal to 1. But that's my k. So when you go to your flowchart, when k is 1, we have an inconclusive test. So all this work I just did was inconclusive. So if I was absolutely insistent on determining whether this is convergent or not, I'm actually going to use the limit comparison test. Let a sub n be the original sequence. Create a new sequence, b sub n, that's just get rid of the clutter. Get rid of the non-dominant terms, which simplifies to 1 over 4n. Then you do a limit of a sub n divided by b sub n. So a sub n is n plus 2 over 4n squared plus 3n. And instead of dividing by a fraction, I'm going to multiply by the reciprocal, so 4n over 1. If you want, you could distribute, and you have 4n squared plus 8n over 4n squared plus 3n. And then you could factor an n out and cancel it, or you could use L'Hopital's rule, or recognize that this is a balanced rational function. This will approach the ratio of the leading coefficients, 4 over 4, which is 1. Now, this 1 I just got is not to be confused with k. The limit comparison test, this is what we're calling the L. And careful not to use the same letter, because they don't have the same flowcharts from this point forth. When you're doing the limit comparison test, all that mattered was that L was positive and finite. If L is positive and finite, then we know that the series of a sub n and the series of b sub n behave alike. So we further have to say, okay, what do I know about the series of the simple one? The series of b sub n is just 1 over 4n. This diverges by the p-test. Therefore, the series of a sub n, which is the original one, diverges as well by the limit comparison test. If you're doing a limit comparison test and you get L is equal to 0, that's inconclusive because L has to be positive. But if you do a ratio test and you get K is equal to 0, that's okay. 0 is allowed for the limit of K, and you still can lead to this conclusion. So there is some potential for confusion here. Just make sure you know which flowchart you're looking at and what the acceptable limit values are. All right, one more ratio test. There's factorials and n to the n's. This is a clear case of use the ratio test. Also, n to the n dominates 4n factorial. So as a sequence, this does approach 0. Therefore, as a series, there's potential for convergence. If you had flipped these around, by the way, as a sequence, that goes to infinity. So as a series, it would be divergent by the divergence test. But the way it's written, there's potential for some convergence here. Okay, I'll begin by rewriting the sequence, but use n plus 1s. This is an absolute value, times, and then rewrite this, but reciprocate it. Now, these terms are already all positive, so the absolute values here really aren't needed. And the 4 and 4 will cancel. N plus 1 factorial over an n factorial. I'll put the factorials over each other. And then we have an n to the n. This term I need to write still. And I'm going to do the trick where I break this up. If you have a power that's n plus 1, then I'm going to do this to the n and then this again, but to the 1. N plus 1 to the n, and then an n plus 1 to the 1. Let's simplify the factorials next. N plus 1 factorial over n factorial simplifies to just n plus 1. So we have an n to the n over an n plus 1 to the n. They're both to the n, so I'm going to write this. N over n plus 1, that's all raised to the n. And then we still have this extra 1 over n plus 1. And we get more simplification. All right, if this doesn't really simplify any further, the base is approaching 1 while the exponent is getting larger. 1 to the infinity is actually an indeterminate form. We need to do some manipulation here and then L'Hopital's rule to figure out this limit. All right, we're going to use the strategy of if ever you have something to a power, you can write this instead as e to the natural log of that thing, and then use the property of logarithms to bring that b down. I'm going to use this on this sequence. Now I'm going to analyze the exponent. The n is approaching infinity. Inside here, this is n over n plus 1. That's approaching 1, but the natural log of 1 is 0. So this is still an indeterminate form, but it's a product indeterminate. And the easiest way to turn a product indeterminate into a quotient indeterminate so that you can use L'Hopital's rule is instead of multiplying by n, divide by 1 over n. Now, this is approaching natural log of 1, which is 0, and as n goes to infinity, we get 1 over infinity, that's also 0. We have something that L'Hopital's rule can be used on. Now, before I actually do L'Hopital's rule, I'm going to do a property of logarithms. If you recall, if you have log of a over b, you can do log a minus log b. I'm going to use that property on this exponent first. It will make the derivative much easier. So natural log of n minus natural log of n plus 1. Now, I'm going to do L'Hopital's rule. Derivative of the top, 1 over n minus 1 over n plus 1. And the derivative of the bottom is negative 1 over n squared. All right, next I'm going to recombine these into a single term. So I had to get a common denominator, which means, right, I'm going to have to multiply this fraction by n plus 1 over n plus 1, and this fraction by n over n. In the top, we get n plus 1 minus n. We get a 1 up top, and the bottom is an n times an n plus 1. And then instead of dividing by this, I'm going to multiply by its reciprocal. All right, this is equal to e to the negative n squared over n squared plus n. This is a balanced rational function now. So as n goes to infinity, a few more L'Hopital's rules here will confirm that this approaches negative 1, which is the ratio of the coefficients. This approaches e to the negative 1, which is equal to 1 over e, and this is our k. Go back to our flowchart. 1 over e. Well, e is between 2 and 3, so 1 over e is between 1/2 and 1/3, but it's definitely less than 1. Therefore, we know the series is absolutely convergent. Since k is less than 1, the original series is absolutely convergent by the ratio tests. All right, so that was a little bit more of a complicated example. This kind of thing will typically happen when you have an n to the n involved. Okay, now the root test. This will conclude our tests. If you're working with a series, take its sequence, raise it to the 1 over n, put it in absolute values, and simplify that and do a limit as n goes to infinity, and again, approach k. Now, the flowchart for the k here is the same. That's why I'm using the same letter. But the nice thing about the root test is that the conclusions for its k are the same as for the conclusions for the k of the ratio test. The root test is a useful test to use instead of the ratio test when everything's being raised to the n, like both things here being raised to the n. Also, look at this. This is an n to the n, and here's a fixed number to the n. N to the n dominates, so it's going to grow much faster, meaning that, right, as a sequence, this is approaching 0. But we still don't know as a series converge or diverge. So we're going to use the root test here. It's probably a good idea to recognize that everything here could be just written as negative 2 over n, all raised to the n. And when you see that your sequence is something all raised to the n, then this is a good test to use because when you do the nth root, you're going to cancel that power. All right, so we begin by just rewriting this. Then we're going to raise all of that to the 1 over n, and then do the absolute value of all that. When you have something raised to the n and then you raise to the 1 over n, you multiply the powers, so those cancel. This takes us to just negative 2 over n, but that's in an absolute value. So that takes us to just 2 over n without any absolute value needed. We do a limit now as n goes to infinity. This approaches 0. That's our k. That's top case. And so we know that the series is absolutely convergent. Thus, this series absolutely converges by the root test. This series also has negative terms involved because we have an alternating sign effect here. So if this had been a plus, it would still be convergent. That's what the definition of absolute convergence is. All right, this next one here, this is a clear case of, again, everything's raised to a power, so use the root test. So we do an absolute value, so bracket 3n over 2n plus 4. So there's our sequence, and we're going to raise that to the 1 over n and then do the absolute value of all that. The absolute values will cancel because there's no negatives here in play. The n and 1 over n will cancel, so we're just going to get 3n over 2n plus 4. Don't cancel these n's, right? That's a bad simplification. But this is a balanced rational function. L'Hopital's rule will confirm it goes to 3/2. This is our k. This is more than 1. Thus, the original series diverges by the root test. Okay, so that's a fast one. This one here will be pretty fast as well. Absolute value, bracket, write down the sequence, n bracket, raise it to the 1 over n, absolute value. This will just simplify to n over n plus 4. This approaches 1. This is our k. Inconclusive. We need another test on this. The root test isn't going to do it. I'm going to just analyze this as a sequence. I'm not sure what this is even doing. It looks very similar, though, to the time we spent doing that sequence. The only difference is that there's a 4 there instead. I'm going to copy this work, and we're going to actually just edit it. Let's go through here and make some changes. That's a 4. Okay, this is, as a sequence, it is approaching a 1 to the infinity. So this is an indeterminate. This would be a 4. Here, this is approaching infinity times the natural log of 1, which is 0. So it's still a product indeterminate. So we still get to do this next stage, except that will be a 4. This is approaching 0 over 0. So again, we get to do L'Hopital's rule on that exponent. But before I do L'Hopital's rule, I'm going to break up this natural log. So this will be a 4 there instead. This will be a 4 here, and these should therefore be read n plus 4s in order to get a common denominator. So when I multiply n plus 4 times 1 and then subtract n, I'm actually going to get a 4 up top here. So there's going to be a 4 joining this n squared. So this will approach e to the negative 4, which is 1 over e to the 4. But we're not doing the ratio test here, so this is not a k. We're analyzing this as a sequence. So all this work was to show that this sequence, since it approached a 1 to the infinity, which is an indeterminate, I had to do all this work here to show that ultimately it approaches a 1 over e to the 4. But this is not 0. Therefore, when you add them all up forever, you're adding up something that's not 0 forever, which will add to infinity. Thus, the original series diverges by the divergence test. It just took a lot of work to show that this did not approach 0. All right, that wraps up all the tests that we are going to learn. There's a review sheet that I've put together. It summarizes all the tests that we've learned, tests 1 through 9. Gives us a conditional and absolute convergence summary. Domination chain is given. Comment on the only series that we can find sums for without using technology, that is. That's the geometric series. This is the only series that we had a formula for giving the sum. All the other series that were convergent, we had to use Desmos to approximate the answer. All the other series we've seen, we've just been content to say whether it was convergent or divergent or conditionally or absolutely convergent. Also on this are 16 problems. I do recommend that you do all 16 of these as preparation for your test. This is a good stopping point to take a breath, do this sheet, and feel like you have a good firm grasp of all 9 of these tests.